Hello, I'm Mr. McBrien. This is TEJ20, hexadecimal numbers. The Ontario curriculum wants us to be able to describe how computers represent and process data using the binary number system. We're going to actually realize that the hexadecimal number system is very important to using the binary number system, and for this reason we'll also study it.
The number 16 isn't a natural counting base for humans with their 10 fingers. In fact, of course, 10 is. It does appear a lot in human society because of its unique properties. It's an exact square. It's 4 to the 2. It's 2 to the 4, something we're going to exploit very soon. There's lots of other fun things about the number 16, including the layout of the chessboard. All of that stuff is very interesting, very fun. But we're interested in 16 for another different reason. We saw yesterday that computers can only store and manipulate data in a binary base 2, yeses and no's. And nothing about that has changed. The earliest computer programs were written in binary, if you can imagine this. Imagine highly trained mathematicians inputting zeros and ones. But these skilled individuals made lots and lots of mistakes. And the reason why is a phenomenon called confusion camouflage. The human eye becomes confused when it looks at large groups of similar looking objects. So when confronted with lots of zeros and ones, mistakes happen. So early on, it was discovered that we needed to be able to convert large binary numbers, groups of ones and zeros, into something that humans could read and manipulate accurately. Now, they could have decided to convert to base 10, to decimal. But the conversions between base 10 and binary, and between binary and base 10, we've already seen are mathematically difficult. They take a lot of time and effort. What we're going to see is that converting to base 16 is in fact much easier. But first we have to understand what base 16 implies. Now keep in mind, you can go online and you can get calculators to do conversions between the numbers. And this is fine, but you must be able to make these conversions manually for the tests in computer engineering. And in fact, that exercise of going through those tests will help you to better understand the implications of these things. So perhaps it won't surprise you that we go right back to this kind of a table of numbers, table of digits. So whereas in decimal we had 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, etc. And in binary we had 2 to the 0, 1s, 2 to the 1, 2s, 2 to the 2, 4s, and so on. In hexadecimal it's 16 to the 0. In other words, our rightmost digit is the 1s. The second rightmost digit is the 16s, then the 256s, etc. Otherwise, this table is identical to the other ones we've seen so far. But wait, we've got a problem. Okay? We only have 10 characters for numbers because we developed having 10 fingers. So in fact, we need 6 more characters. So we have to add in some characters for the numbers that can't be covered by our original decimal system. And we use uppercase A, B, C, D, E, and F for those other numbers, so that we can have up to 15 in the ones column. Now, you've probably already seen computers displaying hexadecimal numbers where it's needed. So in this case, we have a background color of 99FF66. And you'll see lots of these examples of hexadecimal displays if you start watching for them. We're going to better understand hexadecimal numbers by doing a little bit of work together. And we're going to start, unlike in other cases, we're going to start just by simply counting. So we're going to count in hexadecimal, and it's going to start out, it's going to be extremely boring. Because decimal, we would start with 0 and go through to 7. And in fact, in hexadecimal, we do the exact same thing. And we can continue. The next number is 8. And the number after that is 9. The difference comes when we get to decimal 10. In hex, we don't reset. We don't move to a second digit. We can still represent 10 with one digit. So what do? We, of course, choose A. And from there, it's B, C, D, E, F. And now we've used up our 16 unique characters. And the next thing we do after that point, since we've used up our 16 characters, we have to move to using 2 digits to represent our number. And maybe some of you have guessed. The next number then, decimal 16, is hex 10. And what does this mean? It means 116 plus 0 ones. And then we can continue counting from there, and the numbers look just like decimal numbers. And we continue along there until we diverge again when we get past the number 9 and get to A. So what I would like you to do is I'd like you to pause the movie right now, get out the homework sheet, and just do some counting. You'll be surprised how useful this is, and it will become second nature pretty quickly. So go ahead and move through counting in hexadecimal. And certainly at first it's going to look strange to you. Okay, welcome back. Hopefully you finished the counting exercise. Now we're going to talk about how to convert hex to decimal. We're going to use the exact same process we saw yesterday. So when you're working with hexadecimal on a test, draw the table in ink and use that conversion table. So all you have to do is learn how to make that table, and the rest is really pretty straightforward. Okay. So here's our table here with our first example problem. Convert F01 to decimal. Now our table starts out with the 1s, the 16s, the 256s, and the 496s. Sorry, 4096s. And we write in F01. Now, what we're really saying here is we have 1 1, 0 16s, and F 256s. So you have to be able to convert that F to decimal before you can use your calculator. So F is in fact 15 in decimal. So we know we have 15 256s. We get out our calculator, and that converts to 3,840. 0 times 16 is 0. 1 times 1 is 1. Add them together, and we get our decimal number. 3840 plus 0 plus 1 equals 3841. So this is just like the process in binary, except we may have more than just 1 or 0 in the given boxes. So let's try another one. Let's convert 5F7B to decimal. So the first step is to erase the previous pencil letters from the last problem we worked on, and then write 5F7B into the appropriate columns. And once we've done this, we just simply have to multiply. 5 times 4096, 15 times 256, 7 times 16, and B, or 11 times 1. Let's see if I got it right. 5 times 4096, 20,480. 15 times 256 is still 3840. 7 times 16 being 112. And 11 times 1 being 11. Add them all together, and we get our decimal version of 5F7B. Now this starts to point out to us how much more efficient it is, how much more condensed a number is if we have hexadecimal. It's only 4 digits in hexadecimal, but it's in fact 5 in decimal. Okay, I went through that quickly, but I'm pretty confident you can work through it. Go through the practice problems and do at least some of those on the homework sheet before we get to the harder part. Welcome back. Hopefully you had some success with converting hexadecimal to decimal. Just like with converting decimal to binary, we have to use the opposite process to convert from decimal to hex. So, the conversion table is still our best friend. So hopefully you've got that in ink and ready to go when you look at this. Here's our conversion table. And what we need to do now, once we have a problem in hand, for example, what's decimal 78 in hexadecimal, is we have to actually do a process of division. Now, for starters, we should be able to recognize that 78 is smaller than 4096, so we don't need any of those. Smaller than 256, we don't need any of those. But it's bigger than 16. Now, unlike the binary case, we don't just simply write in a 1 here. We need to do division. So we divide 78 by 16. And the number we get is 4.875. So when we see this, we know that we need 4 16s in order to represent 78. So we write the 4 in, and then we have to consider what's left over. So you can either use the remainder that you see there, or you can go ahead and multiply through and subtract. But you have to find the amount of the number that's left over. So 4 times 16 is 64 by my count. We can subtract the 64 from 78 and get 14. So 14 is how much of the number we need to represent in the ones column. Now, if you're writing a 14 here, you're going to get part marks, but you're not going to get full marks. And the reason should be obvious to you by now. The 14 isn't an appropriate character in hexadecimal. We need to convert that 14 to an E. And so the full answer, 78 in decimal, is 4E in hexadecimal. Should we try another example? Decimal 254 in hex. All right. Again, we're not going to need any 496s. We're not going to need any 256s. So no 4096s, no 256s, but 16s we will need. So we divide 254 by 16, and we get 15.875. So we know we need a 15 in the 16s column. We need 15 16s to represent 254. But we can't leave it like that. We have to convert that 15 into an F. When we're finished that, we have to figure out our remainder. So 15 times 16 is 240. The amount remaining is in fact 14. And the 14, of course, we again need to replace that with an E. So in order to represent the number 254, we need F 16s and E 1s. So decimal 254 is FE in hexadecimal. So go ahead and do some of those practice problems, please. Pause the movie and come back when you've done a few of them. All right, welcome back. So now we talk about converting hex to binary. In fact, converting to and from decimal wasn't why hexadecimal was created. This number system was created for the problem on the screen right now. It was created because it's easy to convert to and from binary. So what you're going to find is once you're used to them, these conversions are quicker and more efficient than anything to do with decimal. Because that's what this number system was made for. So the reason why is we don't have to do that remainder process. Things will always come out even. So 4-digit binary numbers, we refer to these, we have a special name for them because they're so useful. We refer to them as nibbles. And a 4-digit binary number will convert 1 to 1 with a 1-digit hex number. There's never a remainder. Why? Because 4 binary digits can represent all the numbers from 0 to 15, just like hex can. And again, this is why hex exists. So, if we look at binary then, we know that we can represent with binary all of the hex numbers with 4 binary digits, adding zeros to the left-hand side where we need to. This table is so useful, you may decide you want to memorize it. Or you can go ahead and do conversions all the time. You can use decimal to do the conversions, but you must be able to convert the numbers between 0 and 15 from binary to hex and from hex to binary. Now once you can do this, since the nibbles map 1 to 1 with hex digits, all you have to do is create a binary nibble for each hex digit in your system. And just be careful about the order. The order of the numbers is extremely important. So let's try an example. Here's a 3-digit hex number. So as soon as we see it's a 3-digit hex number, we know it's going to be a 12-digit binary number. 3 times 4 is 12. And all we have to do is convert each digit. If you remember the table from previously, F converts to 15, which converts to 1111. 4 is, of course, decimal 4, which converts to 0100. And F is still 1111. So these conversions, you'll probably find they're pretty easy very quickly. But we have now just converted a 3-digit hex number to binary. All we have to do is write them down in the correct order. F, 4, F. And there's our conversion. No messy multiplication and division. No remainders. Let's try a second example. A 5-digit hex number. Converting this to decimal would take a great deal of time because it's a very big number. However, we now know that this is going to convert perfectly to a 20-digit binary number. So, the first step, convert each digit. A is the same as 10 in decimal, which is the same as 1010. B is the same as 11, which maps to 1011 in binary. 0 is just 0, but make sure you keep all 4 digits. 0 is again 0, and we keep all 4 digits. 2 is in fact 0010. And we're done. We have our 20 binary digits. We just have to make sure we write them in the correct order. So AB002 is the same as, and I'm not going to bore you by reading out all of those numbers. But do remember, the zeros are important. If you accidentally map, for example, this 2 as just 1 0, your number changes dramatically. So don't leave the zeros out. Alright, so as far as practice goes, you can do the hex to binary conversion section of the worksheet. It's pretty quick. Now, converting binary to hex, the only catch is making sure that you work right to left. So you're going to divide the binary number into 4-digit nibbles and then work accordingly. Okay, so let's try one. 110110010 in hex. So the first step is to divide into nibbles. All right, we work right to left. So we take the rightmost 4 digits, make that a nibble. The next 4 digits, make that a nibble. And in this case, we have 1 digit left over that becomes its own nibble as well. So we know we're going to have 3 digits in hexadecimal. Now we convert the 3 nibbles into hex. 0010 maps to 2 in decimal, which is of course 2 in hex as well. 1011 is 11 in decimal, which maps to a B. And 1 is a 1 in decimal, and in fact a 1 in hexadecimal. We now have our 3 hex digits, and we just have to write them in the correct order. So 110110010 is the same as 1B2. Should we try another example? Okay, first step, divide into nibbles. Here are our 3 nibbles. Second step, convert each nibble into hex. The first one is a decimal 10, which maps to A. The next one is a decimal 14, which maps to E. And the final one is a decimal 3, which maps to 3. Then all we have to do is write them in order. So that big string of binary digits is the same as 3EA in hex. Okay, so go ahead and work through the rest of that worksheet. And I think you'll find that it's much more pleasant once you're used to it, converting binary to hex and hex to binary than it is using decimal. Now, a last note before we finish up. Remember that computers do not store hexadecimal. Everything is stored in binary. The computer just converts to hexadecimal so that the silly humans can read it okay. Alright, so key points for today. Computers store and manipulate values in binary, but usually display them for us in hexadecimal format. Each group of 4 bits, each nibble, corresponds to 1 hexadecimal digit. The hexadecimal digits run from 0 to 9, A, B, C, D, E, F. And when we build our list of digits for hexadecimal, each time we multiply by a factor of 16. Hexadecimal values, by the way, are usually followed by a lowercase h or a small 16 to let us know that they're not decimal values. Okay, so for your homework, please go through and work through as many of those problems as you feel you need to, and check your answers using the answer key. Now for fun, you probably remember quite well our discussion about IP addresses. An IPv6 address is 8 4-digit hex numbers. I invite you to do the algebra challenge. Try to calculate how many unique IP addresses there are. And you may find this kind of stimulating to do, certainly very interesting to see. Thanks very much. Have a great night.